hope you're doing well. This is our fourth lesson in the probability unit. Today we're going to talk about dependent and independent events, and we've kind of been referring to independent events since we started talking about probability, but let's get into it and see what it's all about. So compound events we talked about already, and that's when you have multiple events occurring within one overall event. So if you tossed a coin multiple times, for example. And in some situations with probability, like tossing a coin, let's say a coin is tossed and lands head, what's the probability that the second flip will also turn a heads? Well, the first flip is 1/2, obviously, it's 1 out of 2 chances, and then the second flip's the same thing, where it's 50% or 1/2. This is what we would call an independent event. It doesn't matter how many times you flip it, you always get the same chance every single time that you flip. So it doesn't change, and we'll talk about when it can change, not with coins, but in other situations. So let's say a coin is flipped 4 times and turns up heads each time. What's the probability that the fifth trial will also be heads? Again, it doesn't change. It's 50% or 1/2, or you could say 0.5. And if we wanted the probability of that just to try it, so let's say we had 5 heads, you would have 1/2 times 1/2 5 times. Or 1/2 to the exponent 5, which gives me 1/32. And we talked about a situation where if you had a mixture of heads and tails, then that gets a bit more complex, but we're really just focusing on what's independent. And so if one event has no effect on the occurrence of another, it's said to be independent. So there's lots of situations where that occurs. For example, simple things like if you spin a spinner, and there's some questions in the textbook about that, with colored spinners, you always get the same chance each time. Or if you're rolling a die, it's supposed to be random and independent each time. Even when you're drawing a card from a deck, if you replace it, so if you put it back in the deck, so put the card back, then it remains independent. You get the same chance each time. So if I draw an ace, but I put it back in the deck, then I have an equal chance again of getting an ace, which would be 4 out of 52. Or if you roll one die twice, like we were saying, you get the same thing. So we talked about this multiplication rule, and we had it when we were dealing with combinations and permutations, but it really holds true for independent events as well. If you have the probability of one event and another event, you're going to just multiply those two events together, the probabilities. And that looks like the intersection. So this thing is the probability of A and B. So for example, what's the probability that when you toss a coin 3 times, you land a head 2 times and then a tail? And in fact, it's a head and a tail. That would be like 3 separate events, all within one larger event. And really what you're doing, if you think of it as probability of head, tail, and in that specific order, then you're doing the probability of the first event, which is a head, times the probability of the second event, times the probability of the third event. And each one of those, the head, and tail, each has 1/2 of a chance. So you get 1 out of 8. And in this case, the order does matter. If it didn't matter, if they said, you had to have 2 heads and 1 tail and the order doesn't matter, then it's a different question. So in those simple examples, you're just multiplying through, and we'll look at a couple other examples. But it is important to note that if you're doing one event and then the next event, you're multiplying. But if it's one event or another event, then you have to add. So let's say you toss a coin and then you roll a 6-sided die. What's the probability of getting a tail and a 5? So in this case, they're combining these two into one overall event. So I've got the probability of tail and a 5. So I simply take the probability of the tail times the probability of the 5. So we have 1/2 for the probability of a tail, and the 5 we have 1/6. So we end up with just 1/12. So This and part tells me that they're going in succession. And if I change that to getting a tail or a 5, then like before, I'm now into this or situation where it's one event, so the probability of a tail, plus the probability of the other one, the 5. So I've got 1/2 plus 1/6. So 1/2 because that's the probability of a tail, and this 5, there's 1 5 on a 6-sided die, so it's 1 out of 6. So if we make a common denominator here, we can just add these together. And we get 2/3. So very different outcomes, and you just have to watch for that if they're combining things. But this can be extended, this idea of multiplying these two independent events. They can be completely separate things, but you can still include them within the likelihood that you know something's going to happen. So for example, let's look at this next one. It says Katerina estimates the probability of passing math is 0.8 and the probability of winning her volleyball game is 0.9. It says find the probability that Katerina will, and then so pass math and win volleyball. So we've got and here, so we've got pass math, so pass and win, let's say. So we know that that's going to be the probability of the pass times the probability of the win. So every time you multiply by another chance of something happening, your overall chances start to go down. So if I take the probability of pass, which is 0.8, times the probability of winning, which is 0.9, there's a less of a chance that both of those things happen. So we're down to, if we multiply those together, 0.72. And you can play around with this kind of thing, and let's say it's probability of pass math but lose volleyball. So first thing you have to think of, well, what's the probability of losing? And that's just the opposite, or rather the complement of winning. So it's going to be 1 minus the probability of winning, which gives me 1 minus 0.9 or 0.1. So if I want the probability of pass and I know it says but lose volleyball, but they're still combining them together. Doesn't always have to say explicitly and to mean that. So pass and lose. I now have the probability of pass times the probability of losing. And if you need to, you can pause the video, obviously, to catch up in the writing, but try to make this a bit quicker. So I've got 0.8 times what we figured out on the left there, 0.1. So I get 0.08. So not a great chance that the two things happen combined. And then the last one, fail math and lose volleyball. This time it does say and explicitly, so fail, and lose. So one thing I didn't mention, but these are obviously independent events. Like one doesn't impact the other, at least that's what we're assuming. I guess there's an outside chance that one could impact the other, but we're going to assume that they don't. So I'm going to take the complement of passing, so failing. So it was 0.8 to pass, so that makes failing 0.2. And then the lose we already figured out, 0.1. And we get a 0.02 chance that that's going to happen, or 2% chance that works out. So independent events, nice and easy because you can just multiply them together. There's not a lot of extra thinking. Sometimes you have to use this complement stuff, but overall it's not so bad. There are other situations which are the opposite of independent, which are called dependent events. And sometimes when you know more information, it changes the likelihood that the next event might happen, or it directly impacts. And so you actually end up having to adjust what the second outcome would be. And I'll explain some examples here, and I think that helps. So, for example, the weather, if you know it's going to be cloudy, then you know that there's a more likelihood chance of rain. It's not going to rain generally if it's not cloudy, although that does happen. Or if you're talking about smoking and cancer, if you know someone smokes, then their chances of cancer go up. or lots of all of these underlying medical conditions changes the likelihood of things happening. Or if we were talking about something more related to the course, if you're dealing cards, but you don't replace the cards back into the deck, so without replacement. So if I deal 5 cards out to each person, then clearly I'm not putting them back into the deck, and that impacts the chance that whatever the next card comes up. So we'll look at some examples like this. But let's just start with one here with a Venn diagram. And these ones are very much visual, but we'll also do some ones where we kind of rely on some formulas. So it says, consider the following example. The Venn diagram shows the number of students in a class who study Italian and French. So we've got Italian here on the left and French on the right. Suppose a student is randomly selected from the class and it is found that the student studies French. So we know that they study French. We can determine the probability that the student also studies Italian. This is what's called conditional probability, and it's a dependent event because it is the probability of the Italian occurring, speaking Italian, on the condition that we already know that they speak French. And so you can think about that for a second. So if you know that they speak French, what's the chance that they speak Italian? And so we say it like this. We would say the probability that speaking Italian, given that we know that they speak French or that French has occurred. And it's written like this. So if I use their I's and F's, so I have I, and then we have this line that represents given. So this thing represents something that's given. And so speaking, I would read it as the probability of speaking Italian given that they speak French. So if you look at this, here are I'll just highlight it in different color here. Here are all the French speakers, right? So I know they're getting pulled from this group. And if I know that, then what's my chance that I have an Italian speaking person from that group? So really what it comes down to is that I get the intersection, which is the Italian part. So this part in the middle, those are the Italian speakers who are in the French group out of the total, which is from the French group, in this case, the 8 plus 7 or 15. So if I have this situation and I know one piece of information, I can then find, what's the likelihood I randomly select someone if I know that they're coming from that group. So that's a very specific example, and we'll do another one like that here in a minute. But these dependent events led to the discovery of this conditional probability, and there's a nice formula that you can often rely on in these situations, and we're going to use it. So the multiplication rule for conditional probability says, if you have the probability of events in A and B occurring, given that A has occurred, so you in the previous example, we know that they were French, is given by this, the probability of A and B. So this is my and again, it's the intersection, is equal to the probability of A times the probability of B given A. So this probability of A and B is equal to the probability of A times the probability of B given A. So this part here is the probability of B given that we know A. And this can be rearranged in order to find that conditional probability. So let's say I wanted to find the probability of B given A. I could write it like this, and I simply rearrange that formula so I have the probability of A and B over the probability of A. And whatever the second thing is, the B given A, this will always be corresponding to what's in the denominator. So just something to watch out. And we'll see some examples like that. Let's go back and try another example similar to that one with the Italian and French speakers. So it says in a class of 25 students, 14 like pizza and 16 like iced coffee. One student likes neither and 6 students like both. One student is randomly selected from the class. What is the probability that the student likes pizza? So we can use a Venn diagram if we want here, but in the first one, I'm not sure we need it. So in A, probability like pizza, and they're saying from the whole class. So we've got 14 like pizza. So we know that this is just going to be 14 out of the total, or 25. The second one, though, is a bit trickier. It says likes pizza given that he or she likes iced coffee. Well, I am going to create this Venn diagram to show this. And I think it can help. But we'll look at it in two ways. So let's say we've got the pizza and the iced coffee. And we can fill this in. So we know that one student likes neither. So one person is out here. 6 students like both. And then we can figure out, so we got 14 who like pizza, so that means 14 minus 6 gives me 8 for this, so that's 14 minus 6, because that total from the pizza needs to be 14. And similarly on the iced coffee, we've got 16 minus 6, which is going to be 10. And so if I was to add those up, we should get a total number of students of 25, and that includes this 1 on the outside. So let's say we want the probability of liking pizza given they like iced coffee. So in this case, again, you can kind of think of, I know that they like iced coffee, so I've got this whole thing, right? I'm looking at them. So I'm only considering those people. So of those people, how many like pizza? And so I've got 6 as the intersection out of 16. And if you go to the formula, so we can obviously reduce that if we want into 3 over 8. But if I go to the formula, you can also think of it like this. I've got probability of B given A, so which in this case would be the pizza given iced coffee, is probability of pizza and iced coffee over the probability of the second thing, which is the iced coffee. So the probability of P and iced coffee would be 6 out of 25. And the probability of iced coffee is 16 out of 25. And so what happens when you do the math of this, those 25s cancel out, but I'll just show it in a couple steps. I have 6 over 25 divided by 16 over 25. And with a fraction and we're dividing, we got to flip that second fraction. And so the 25s cancel out. And we get the same answer. So the visual, I think, is nice to work with, but you can also rely on the formula for that one. Okay, let's try a couple other ones, and then you'll get to try some for the homework. It says the probability that Maurice will go to Western is 1/5. The probability that she will go to another university is 1/2. If Maurice goes to Western, the probability that Guy or Guy will also go is 3/4. So Maurice going to Western will influence whether Guy goes to as well. So what's the probability that both of them go to Western? This is where I think using the formula is really important. So if you consider A as Maurice going to Western, and I think it's helpful to write out these things, then I know that the probability of A is 1/5. So that was given. And then let's say the second thing is B is Guy going to Western. And we know in this case, not that probability, but we know the probability of B given A is, if we go back here, is this, the 3/4. So the probability that Guy go if Maurice goes. So what they're asking for in this case is the probability that both will go. And what that means is the probability of A and B. So both will go to Western. So relying on the formula, the probability of A and B is equal to the probability of A times the probability of B given A. And often these questions, it's almost always going to be that you divide or you multiply. And if you know what you're looking for, the A and B, you're going to be multiplying. If you know that you're looking for B given A, you know you're going to be dividing. You just have to figure out which ones. And that's where I think listing these things on the left, like A and B, can be helpful, and you can use the formula. So if I just write these in, I got 1/5 times 3/4. And so we have a smaller chance here, so I'm going to have 3 out of 20, which is equivalent to 0.15. And you could leave it as 3 out of 20 if you wanted to. Okay, one more question here. This one's a bit different. It's more of a logic one, and you could probably answer this one in a couple ways, but we'll try to use this conditional probability to answer it. It says a study of telemarketing companies' data showed that of 1,000 calls placed, the experimental probability of a call receiver staying on the line for at least a minute was 16%. So you know how you get these calls and they're trying to sell you something or doing whatever. And so the chance that someone stays on the line for at least a minute was 16%. The conditional probability of a call resulting in a sale, given that the receiver stayed on the line for at least a minute, was 10%. So that's telling us that we've got a conditional probability. So they have to stay on the line. So it says no sales were made if the receiver did not stay on the line for at least a minute. So it's kind of the assumption in that case. How many sales were made? So let's kind of break it down. So we know that, let's say A is the caller on the line for at least a minute. So it's the probability that we want. And B is the probability of the sale. So the probability of A is 0.16, and the probability we know of B making a sale, given that they stay on the line, that's this 10% or 0.1. What we want is the overall probability here that they stay on the line and make a sale. So that's really the probability of A and B. So again, when it's A and B, you're just multiplying those two things together. So I'm going to take the probability of A times the probability of B given A. So 0.16 times 0.1, which gives me 0.016 or 1.6% chance. And in the end, they asked how many sales were made. Well, that gives me the chance of how many a sale. So the number of sales, I'm just going to simply take that number and multiply it by the 1,000 calls. So they had originally said that there are 1,000 calls placed. So we can assume then at a 1.6% chance that this works out to 16 sales. So therefore, there are 16 sales in 1,000 calls. Okay, as usual, please let me know if you have any questions. Your homework here are the textbook questions listed and plus the handout questions below. The textbook doesn't have a lot of great questions in this topic, so I've added some in here. So try those out. There are solutions also in the content library if you need them. Okay.